Okay, today we're looking at projectiles, and the basic idea that we're looking for here is to understand the independent nature of projectiles, meaning that the X motion, the horizontal motion, is completely independent and separate from the vertical motion. So we can analyze those two motions separately using the same four linear motion equations that we've used in the past. So ultimately we were trying to find oftentimes the time that the projectile is in the air, how far does it go horizontally, how high is it, and how high is it at any point in time. So we're maximum height and at any point in time. So we're going to use our linear motion equations to be able to use all of that. But let's first get an understanding of this independent nature of projectiles. So if we had an object and we were throwing this ball, let's say, horizontally, and let's say it was throw it horizontally at, I don't know, 2 meters per second. So if we were to draw that each second, it would be here, and then say here, and then here, and so on. And the spacing of that would be equally spaced at each second. You know, each distance between here would be 2 meters. But if we also took a second ball, and I'll just leave this one here, and we dropped it, well, if we start from initial speed of 0 in the y direction and let it fall, well, in 1 second it would be here, and in 2 seconds it may be here, in 3 seconds it would be further down, in 4 seconds it may be way down here, and in 5 seconds it may be off my page. But if we had these two motions happening at the same time, then in 1 second the object would be here because it's going over and falling, and in the next second it would then go over and down, and it would be, say, here, and in the third second we're now here, and in the fourth second we are here. So it makes this sort of half of a parabola path, and this path we call the trajectory. So the trajectory is the path that an object or a projectile follows. So what's happening is that the ball is moving independently horizontally at the same time it's falling down. So we're going to be able to use those two concepts to be able to analyze problems. So remember that we have four key equations. Let's just refresh those to pull those back. So we know that the average speed is equal to distance over time. And here in the x direction, we have no acceleration. So all the problems we're going to do in here involving projectiles is that we're going to have no acceleration in the x direction. That's not to say that we can't. You know, some of the long-range missiles and so forth that we use, we can have this acceleration in the x direction. But for our purposes, we're looking at projectiles that are launched and then are on their own. So x direction, always for us, no acceleration in the x direction. We also have the acceleration is equal to Vf minus Vi over t, so change in velocity over the change in time. We also have that d is equal to the initial velocity times time plus 1/2 at squared. And then we also have the 2ad is equal to Vf squared minus Vi squared. So these three equations we're going to use in the y direction. Okay, so y direction, remember, is up down, x direction, remember, is horizontal. Okay, so you know, you should be very comfortable with these equations by now, but we're going to continue to use them and continue to build on them.